Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thanks, Anna, for the introduction. Hello, everyone. A very good day, and thank you for joining the AI, the Machine Learning in 5G Challenge webinar series or webinar session. My name is Thomas Baskol from ITU, the International Telecommunications Union. The Machine Learning 5G Challenge aims to provide a community or to create a community to solve network-related problems using AI and machine learning. Today, I'm very excited to host yet another webinar with the title Network Traffic Classification 3.0. This webinar discusses the breakthroughs in network traffic classification and the power of explainable AI techniques. So we are going to discover how these advances are revolutionizing network management, user experience, and privacy. As always, counting on you, everyone who is connecting today, to help create an engaging discussion. And if you have a question, please type them in the video or in the Q&A. And of course, we are going to take these questions at the end of the talk. Without further ado, I would like to introduce the speaker of today's webinar. So the session today, the speaker is none other than Domenico Chionzo, who is the tenure-track professor at University of Naples, Federico, Italy. And thank you so much, Dom, for making time. I know you are not new, you are not a guest here, you have been here with us. So thank you for making time this time around to come and talk to us about the advances in network traffic classification. Good afternoon to you.
Thanks for the invitation. So may I start? Can I start?
Yes, please, the floor is yours.
Okay, you should see my screen.
Yes.
Okay. Hello everybody. First of all, many thanks again to the ITU people for this kind of invitation. Today in this webinar, I will provide you a brief introduction to the design of next generation traffic classifiers via AI techniques, and specifically deep learning. This is a quite challenging and timely topic, and has both the interest of the academia and the industrial partners. In detail, I will first spend a few words describing the context of mobile traffic classification with the current challenges. I will then mainly focus on mobile traffic classification, and I will introduce the application of multimodal deep learning to mobile traffic classification. This is to address the design of classifiers which are able to deal with the heterogeneous nature of traffic. I will then focus on the issues of data availability and reproducibility. This is quite a huge burden in our community. Then I will provide the first shot on the beneficial use of explainable AI techniques to make multimodal deep learning traffic classifiers trustworthy and possibly improve them. And finally, I will discuss how adaptivity can be encoded in traffic classification. And this is achieved by means of the class incremental learning framework. And I will end with some take-home messages drawn from the reported findings. First thing first, why should we care about trying to do analytics from mobile traffic? The reason is that mobile traffic represents a significant share of the traffic generated by devices connected to the internet. Okay, so, and this is highlighted by annual reports like those from Ericsson, Sandvine, and so on. Hence, the design of accurate autonomous network passes through the intrinsic knowledge obtained by a network analytics from such huge bulk of traffic. This corresponds to the perception step in the cognition cycle, which constitutes the main core of autonomous networks. This trend is also reflected in our everyday life. This has changed since the pandemic. And for instance, we have been using massively collaborative apps during these years for working and doing remote meetings, and also webinars like this one. And also there has been a huge increase of the use of video on demand applications like Netflix and so on. And also there has been also a shift toward the complexity of the applications, which now are multi-activity. Hence, to face with the composite nature of the mobile traffic, we are in need of associating network flows being carried over the network with the mobile application that has generated them. Okay, and this is what is network traffic classification, which is the subject of this webinar. Clearly, there are a number of main drivers for performing accurate and effective mobile traffic classification. Such drivers mainly pertain to the main pillars of network management and user profiling. Unfortunately, the situation has dramatically changed, and now performing traffic classification, especially that of mobile devices, has become quite a nightmare for different reasons. First of all, there are hundreds of applications which are currently used by mobile users. We are facing this every day. Just think, what can you find on the Play Store? Each application has its own peculiarities, a bunch of trendy applications come every week and so on. Second, the same application can generate different traffic depending on the device and the operating system it is installed on. Okay, and also its version. So this is a huge diversity. Many applications use common third-party services, which make the identification much more challenging. For instance, think about two applications that are using the same third-party service like Google Maps. And such traffic has become almost entirely encrypted. Okay, so just forget about doing DPI. Of course, network traffic classification problem is not new. Indeed, during the 90s, traffic classification was quite easy because it was performed by looking at the destination port or respecting the payload, or doing both. Okay, and the issues were mainly related to implementation efficiency aspects. DPI resulted to be expert labor intensive and computational intensive. So in 2004, the machine learning techniques came to the rescue. Machine learning allowed to mine common payload subsequences or frequency signatures, leading to stochastic payload-based approaches. Also, machine learning techniques allow to deal with the rise of encrypted protocols and privacy concerns. So, machine learning techniques were designed based on statistical flow features. Okay. Instead, indeed, during those years, both the academia and network players have taken the traffic classification by means of the well-known two-step phase of machine learning, where you have the first phase, there is the definition of a bunch of meaningful statistical features, and the second phase is you design a proper machine learning algorithm for classification based on that feature set. However, this approach has been shown to have serious performance limitations in the case of mobile traffic. Indeed, in the dynamic landscape of today's internet, the effectiveness of this traffic classification approaches face unprecedented challenges. To address the growing complexities, the researchers starting from 2015 have pursued the adoption of deep learning approaches to deal with mobile traffic classification. And this was to circumvent the time-consuming and handcrafted step of feature design. And through joint training of feature extraction classification, deep learning models can achieve state-of-art performance and also enable expert-free updates. So this means that the experts are kept out of the loop. This, of course, holds significantly promise for tackling the fast-paced and dynamic nature of traffic that we want to classify. Despite, however, the achievements in deep learning-based traffic classification, there are still a number of open challenges. These challenges collectively represent the missing link toward the product line implementation of traffic classification techniques based on AI at scale. And this webinar specifically addresses two of these challenges, not all of these challenges, but just two of these challenges. The first challenge, traffic classification solutions designed with deep learning are entirely end-to-end, and since they are data-driven, these make them black boxes. Okay, so network combinators need to understand why a classifier took a specific decision, how much reliable are its outcomes, and whether this could be improved. Okay, and these key aspects are also pushed by regulators. Like just think about the recent AI Act by the European Union. The second challenge is that deep learning techniques are computationally intensive and time-consuming. This aspect is even exacerbated in network traffic classification because new apps or new services emerge every week. And this implies that if a new application or a new service needs to be included, the full retraining of the full classifier is needed to account for the new classification space. So in this context, I will discuss the concept of trustworthy, which is intended to address the first challenge, that is designing traffic classifiers which are interpretable and whose confidence can be relied. This is the first contribution. The second contribution is class incremental learning, which belongs to the more general framework of continual learning and which allows to add new knowledge. In our cases, new knowledge means new classes, new applications, to a deep learning model which is already trained without making a full retraining of the model. Okay. The starting point for our contribution was the state of art in traffic in deep learning traffic classification. The state of art in deep learning traffic classification is currently the use of multimodal techniques because the structure and the heterogeneity of network traffic make it very difficult to address this problem with a single model architecture. So the state of art is currently using multimodal deep learning architectures to deal with this problem. These techniques have shown to be both useful, both effective in terms of performance. So this means that this kind of techniques, multimodal techniques, outperform standard machine learning, of course, but also single modal deep learning and also late fusion combination of deep learning techniques. And also usually these techniques, because they are multimodal, are also usually simpler in terms of the network. So they have lower training complexity. However, there are still a number of issues that need to be addressed. The first issue that needs to be addressed is that whenever you want to make a contribution and to make this contribution shared by the community, and also once it is shared by the community, it is accepted by the industry, we have to, and since these are data-driven methods, we have to carry out this experimentation on reliable and shared datasets. Okay, so the first thing I want to discuss that is an update on our project, which is the Mirage project, which is carried out at the University of Naples Federico II, which is a reproducible architecture for generating mobile app traffic and automatically creating the related ground truth. I'm not going into details of the system. You can look at the paper of Mirage, but just to give a glimpse of what it is a collection and ground truth generation architecture where real users can connect with their devices to an USB hub, which jointly with the capture server is able to collect all traffic generated by them and associate the right app package associated to it. By doing so, we were able to release a first dataset, which is Mirage 2019, which is publicly available and can be used for experimentation. And this dataset contains 40 different applications from 16 categories of the Play Store. This dataset comes with different information for each by flow, like per packet data, the per flow features, and also some metadata. And I would like to update you on the fact that this is an ongoing project. So in the last 2 years, we have also released 2 other datasets based on this architecture, which are Mirage Video and Mirage COVID CCMA. In the second case, we are focusing on the traffic classification of video applications. And in the third case, we are focusing on traffic classification of collaboration and communication apps like Zoom and Zoom Teams and so on. So you can look at the web page and download the dataset if you want to experiment with these techniques. The first contribution is, okay, we have shown that multimodal techniques are beneficial with respect to single modal techniques, but why? So we cannot just bona fide trust that this is true because the experimental data tells us so. So what the reasoning on the proposed numismatic architecture, what it is really disappointing is that it works quite well, but we don't actually know why. So it is of interest understanding what's going on into such black box. However, understanding the internal behavior of neural networks is not only useful to interpret and justify their behavior, but also to troubleshoot and improve them. For this reason, in recent years, there has been a widespread adoption of so-called explainable AI techniques in network traffic analysis. Among the different techniques proposed, there is no general framework, and there is a lack of consensus on which is better. Usually, post-hoc techniques are those which are more used because of their appeal in explaining already trained models, and this is what we have used. Our explainable AI-based framework is defined as follows. For each tested traffic classification object, a byflow in our case, we obtain an explanation by means of the well-known Shapley values, specifically with deep SHAP, of the predicted app confidence when the classifier recognizes the generating app correctly. So whenever the classifier is right, we take the probability associated to the correct classification, and we try to explain this correct probability with the deep SHAP. And once you obtain the explanation in terms of the importance values attributed to each input portion, we normalize them, and this is to have them summing to 1 and attribute the same influence to each byflow explanation. Once we have a normalized byflow explanation, we obtain a global explanation of the classifier by pooling single explanation and taking the median of importance values. By applying the aforementioned methodology, we are able to investigate 3 relevant hidden patterns of mimetic of our multimodal deep learning proposal. But I would like to specify, I would like to underline that this kind of methodology can be applied to any multimodal deep learning technique. First of all, by aggregating the explanation over the whole dataset, we are able to assess to which degree each modality contributes to a correct classification. And it turns out that in the case of mimetic, it is apparent that the payload modality is predominant in recognizing the correct app with respect to the PSQ modality, which collects all the informative fields of the packets, like the packet length, direction, window size, and inter-arrival time. Secondly, by aggregating over specific application, not over the whole dataset, and by looking at the results obtained with the payload modality, it is apparent that the considered number of bytes seem to encompass all the information needed for accurate traffic classification. However, this depends on the specific application. And this, for instance, if you look at Dropbox, the kind of explanation tells us that there is a more structured behavior on the first bytes of the payload with respect to Spotify and Trello. A similar comment also applies by looking at the fields that compose PSQ modality, where all the info seem to be contained in the first 10 packets. So our architecture mimetic uses 12 packets, but it seems that just 10 packets are enough to gather all the necessary information. However, also in this case, the behavior depends on the specific application. For instance, Facebook requires much less packets, left plot, than Trello and Hangouts. The previous analysis underlines that a diversified behavior by varying the application, but a clear imbalance in the contribution provided by each modality. So this means that we would like somewhat to have a much more balanced contribution of the two modalities to the classification outcome. For this reason, we devised an improved version of mimetic architecture, which is named mimetic enhanced, with the 3 key differences. The first difference is that we use an embedding layer for each input, which means an embedding layer for the two modalities. So one embedding layer for the first modality and one embedding layer for the second modality, to make the network fully extract information from each modality without exaggerating the focus on either. Okay. The third contribution is, in order to support a graceful multimodal training, we have adopted an adaptive learning rate, in the sense that the laughter parameter is halved every given number of epochs. This is quite common in state-of-art deep learning techniques nowadays. And this is to avoid instability in training. By looking at traffic classification performance of metric enhanced, we can see that it outperforms all the existing baselines, ranging from tree-based models, but also multimodal classifiers like our previous mimetic proposal. Also, the achieved accuracy is quite general, because if you look at the radar plot at the bottom left of the slide, this applies also to different protocols that are running over the transport layer. And this includes the QUIC, which is commonly used by Google Apps, and also Facebook Zero, which is used by Facebook as apps like Messenger. So it is of interesting understanding what is so special in the behavior of mimetic enhanced to be able to outpace mimetic. For this reason, we compared the modality contribution with our SHA-based framework. Okay, and it is apparent that mimetic enhanced relies in a more balanced fashion on the two modalities. If you look at the bottom plot with respect to the top plot, this is a more balanced importance of the two modalities. And this means that mimetic enhanced is truly able to capitalize multimodality with respect to mimetic. This trend is again quite general, because if you look also at the protocol breakdown, this applies to all the protocols. So it does not apply only to specific protocols. Now that we have explained, we have improved mimetic, there is also the need for understanding multimodal deep learning architecture, to which extent multimodal deep learning architectures are reliable. What does it mean reliable? Reliable means that, for instance, if your traffic classifier tells you that with 90% confidence the byflow that you're observing comes from Hangouts, does it mean that 90% of the times the byflow is generated from that app? So, or the deep learning classification techniques is over-optimistic of this outcome. This is usually assessed by what is called the calibration analysis, and the fundamental tool is a calibration diagram, which is the diagram that you see in the bottom right of the slide. And just to give you an intuition, the more the calibration diagram aligns to the diagonal line, gray line, the better it is in terms of calibration. So whenever the classifier does not align to this gray line, there is either an over-optimistic or pessimistic behavior of your classifier. To improve this, and of course, I want to add this. This is the calibration diagram of mimetic enhanced. So it means that mimetic enhanced is much more explainable, was able to improve mimetic, but its outcomes are not very reliable. So if this says 90% confidence for Hangouts, this is not 90% of the times this will be generated from Hangout. So we investigated two solutions to improve the reliability in deep learning-based traffic classification. The first is based on the so-called focal loss. In this case, the modification relates to a change of the classification loss. Indeed, in the place of the well-known categorical cross entropy, we have used a multi-class version of the focal loss. Though the focal loss was originally conceived for class imbalance, it has been shown in the reference at the bottom of the slide that this can be interpreted as a classification loss, as usual cross-entropy classification loss, plus a regularization term which depends on the entropy of the confidence vector. Thus, this promotes less spiky optimistic outcomes. And it is worth noticing that in this case, gamma equal to 0 corresponds to the usual approach, the usual cross-entropy approach. The second solution that we have investigated is the use of the so-called label smoothing. In practice, during the training phase, the one-hot encoded ground truth is mixed with a uniform distribution by a parameter alpha. This avoids that the trained classifier tries to emulate the hard output of the ground truth. And this promotes a more prudent outcome. And also in this case, alpha equal to 0 means the usual approach. We have to underline that these two solutions modify the training phase of your algorithm. So in principle, they can both affect the traffic classification performance. So you should both verify the reliability, also double check the classification performance. Assessing the reliability of metric enhance in terms of the expected calibration error, which is a synthetic measure taken from the calibration diagram, we now analyze the two solutions that I have described. To do so, we assess the calibration sensitivity by varying the relevant parameters, which are gamma in the focal loss and alpha in the label smoothing. The calibration sensitivity analysis is depicted in the left bar plots, and they report the results on the whole Mirage dataset and also the breakdown by protocol as done previously. Since both techniques modify training processes, as I have said earlier, for each of the considered values, I am also reporting the accuracy and the F measure obtained by making this modification. By looking at the trend of the three calibration metrics, over Mirage dataset, it is apparent that the calibration error shares a unimodal trend, and there is an optimal value. The optimal value is obtained for gamma equal to 3 and alpha equal to 0.025 for focal loss and label smoothing. And this is obtained by looking at the whole Mirage dataset. Interestingly, if we match this result with the traffic classification performance, we can notice that the parameter achieving the optimal calibration does not coincide with the variant that provides you the best classification performance. And in fact, this is indeed for gamma equal to 2 and alpha equal to 0.1 in the focal loss and label smoothing cases. However, the relative loss between these two variants is always very, very negligible, and it is usually less than 0.25%. So by moving these parameters, the outcome is that we can significantly improve the calibration, the reliability of the classifier by only marginally varying the traffic classification performance. By delving into the calibration details of these two variants of metric enhanced, we can compare the calibration diagram of these solutions with the calibration diagram of metric enhanced without any reliability compensating solution. The comparison is performed in terms of the reliability diagrams and also of course, this is more in detail with respect to the expected calibration error. We can also focus on part of the calibration diagram because many of the outputs from these classifiers are in the range 90–10% of confidence. So we magnify this part, and it turns out that the non-perfect of calibration of metric enhanced is balanced when using focal loss and label smoothing. By comparing the focal loss and the label smoothing, however, we can see that the focal loss achieves best calibration with respect to label smoothing, and this is also confirmed by the lower expected calibration error. And this can be appreciated by a direct comparison of the calibration diagram. Also, by looking at the whole prediction range, the calibration diagram of focal loss is much closer to the ideal accuracy confidence line, the gray line. Okay. This can be also drawn by looking at the 90-100% mean. Okay, the bottom figures. And finally, the left table summarizes the results of the calibration analysis. Now it is extended to all the baselines that we have considered. In such a table, for both mimetic enhanced and the best performing baseline, which is our mimetic, we report the results attained with the best calibrated configuration with focal loss and label smoothing, and also without exploiting any calibration technique as a baseline. Okay. The reported results highlight a clear trade-off between the accuracy of the provided prediction and the reliability of the corresponding confidence. Indeed, in its native formulation, mimetic enhanced has roughly 2 times the calibration error of mimetic. So mimetic enhanced improves in terms of traffic classification performance with respect to mimetic, but has 2 times the calibration error of mimetic. So it is 2 times less reliable. Okay. This witnesses that improved traffic classification performance comes at the cost of reduced reliability in provided outcomes. So this calls for methods to improve it. So whenever you want to push the classification performance, you come up with an even better performing solution, you have to make sure that the reliability of this solution is at least comparable with state of art. The second observation is that calibration improving solutions are not always useful, and indeed are less useful when considering an approach which is already well calibrated in its native variant. For instance, when considering mimetic, only label smoothing is able to obtain a calibration improvement, whereas mimetic with focal loss is even less calibrated than its native formulation. Okay. And very interesting, experimental observations also witness that the use of either focal loss or label smoothing, regardless of whether they provide a remarkable calibration improvement, leads to an extremely limited traffic classification accuracy decrease. So this means that focal loss and label smoothing can be used in an effective way with deep learning architectures when there is a reliability problem without affecting so much the traffic classification performance. On the other hand, all the baselines report calibration errors which are higher than mimetic enhanced with the focal loss or label smoothing. And it is worth noticing that the least calibrated approach, which is interestingly also the one that is naturally interpretable, is that represented by decision trees. So decision trees tend to be significantly overconfident with their predictions. Okay. And this outcome highlights the utility of focal loss and label smoothing to improve calibration performance. And for instance, and of course, their usefulness is more limited when considering an approach which is already well calibrated as mimetic, as I was saying before. Interestingly, also, experimental observation witnessed that also the use of mimetic, that the application of mimetic enhanced is able to outperform all the baselines in terms of traffic classification, and also outperform all the baselines in terms of reliability. However, this should be always double-checked. The second challenge that I want to discuss in this presentation is the second requirement that I have mentioned in this webinar, namely whether a traffic classifier can be updated with new applications without a full retraining. Okay. And actually, thanks to advances in machine learning, this is possible. And the fundamental set of tools which allows this solution is called class incremental learning. But first of all, how does class incremental learning compare to a full retraining from scratch? Okay, so I'm now comparing the usual approach with the class incremental approach. The left and right figures illustrate the training workflow in both cases. On the left, we have the scratch approach, the full retraining approach. On the right, we have the class incremental learning approach, the incremental approach. In both cases, at time t, we have a traffic classifier which is usually trained to discriminate among a certain number of classes, maybe applications, services, or whatever. At time t plus small t, t small, we have a new set of classes, maybe new services or emerging new applications that need to be included into classification task. In the usual case, the left case, we have that a new traffic classifier needs to be trained with a dataset which includes both the byflows from the old applications, the old classes, and the new classes. So you collect new data, you build a large dataset, and you retrain everything from scratch. In the class incremental learning case, the previous traffic classifier is updated. So this is in principle computationally efficient. There is no retraining from the scratch, by using only the samples from the new applications. So this is in principle also privacy preserving. Actually, in the class incremental learning case, there are a few subsets of samples from all the classes that are stored to better enforce discrimination between all the new applications. So there is what it is called a small memory, which is kept. So perfect. Let's buy class incremental learning techniques to adapt our traffic classifiers. There is, however, a huge fundamental trade-off which limits the performance of class incremental learning techniques, and this makes them far from performance obtained in the full retrained case. This trade-off is depicted by this figure. Indeed, when we want to update our traffic classifier with new applications, there are two contrasting trends that emerge. First of all, your updated classifier may be not learning in an effective fashion the new application. Okay, so this is called the intransigence phenomenon. The second problem is that your updated classifier may not be retaining the knowledge of the old application. This is the converse problem. This is called the catastrophic forgetting phenomenon. Hence, there is the need for several specialized techniques which have been proposed in the literature, mainly in deep learning literature, to achieve the best trade-off between these two conflicting trends. First of all, it is worth noticing that most of the class incremental learning techniques are devised for neural networks. So most of the class incremental learning techniques are only specific to neural networks, because of their appeal and potential flexibility in incorporating new knowledge. This kind of techniques can be categorized in three main families, which are fine-tuning techniques, fixed representation techniques, and model growth techniques. Fine-tuning techniques adapt gradually both the model backbone and the head during the incremental learning phase. Fixed representation approaches rely on a rich backbone and alter only the model head during the incremental phase. So the feature extraction part is fixed. And finally, model growth approaches enlarge models architecture by enlarging the network to accommodate for new knowledge, in our case, new classes. So here, our first question was to investigate whether there is a case for class incremental learning traffic classification. In other terms, does exist a class incremental learning technique which can approach the performance of scratch? This is the main research questions that we have tried to answer. For this reason, we have carried out a wide benchmarking which includes reasonable baselines and also state-of-art techniques from both computer vision and traffic classification, as highlighted by the taxonomy table that I'm reporting in this slide. By looking at the taxonomy, it is apparent that most of the state-of-art techniques are based on the fine-tuning principle. However, they differ in the way the loss-driving incremental procedure is defined. The general form is that reported in the slide, where there is a classification loss, which focuses on encoding the augmented classification problem to cope with the intransigence issue. And there are also both distillation and regularization losses, which are included to make the updated model behave functionally and structurally like the old model. And this is to cope with the forgetting issue. Last but not the least, most of these state-of-art methods are based on the rehearsal process. In other terms, the forgetting of the old knowledge is mitigated by retaining some samples of the old classes in the model update. Of course, there is a trade-off in terms of privacy and computational efficiency, depending on how many samples are retained in memory, clearly. And equally important, there is also design question on which samples should be retained. In other terms, which is the best sampling strategy from the old dataset. With this large pool of state-of-art methods for class incremental learning, we have evaluated experimentally two different scenarios based on our Mirage 2019 dataset, which contains traffic from 40 different mobile applications. We call the first scenario a big increment scenario, where a traffic classifier is trained with 20 apps and additional 20 apps need to be incrementally learned. This kind of scenario resembles those typically encountered in computer vision in terms of the proportion between old and new classes. The application in this case could be that of traffic personalization, where a given classifier is shared between network operators and one of these operators wants to personalize it with new apps for its billing management operations, for instance. In this case, to provide a little bit stable results, we have evaluated performance on 10 cases of random additions of 20 apps. Okay, so there are 10, we are evaluating on 10 random cases of 20 plus 20 additions. The second scenario is instead what it is called a small increment scenario, where a traffic classifier with 39 apps needs to encode the additional knowledge of a single emerging app. So you have a traffic classifier with 39 apps, there is a new emerging app and you want to include the new app in the classification space. And this is quite peculiar to a relevant situation where a network operator from time to time needs to update the traffic classifier with new incoming apps. In such a case, we have evaluated the performance on the different 40 cases of one-app additions, and this, in this case, provides an exhaustive coverage of all the possible combinations, at least for our dataset. For our experimentation, I would like to recall that in this benchmarking, we have not used any multimodal deep learning architecture, but rather a simpler single model deep learning architecture based on PSQ modality. This is a two-dimensional convolutional neural network proposed by Lopez et al. And the reason is that the class incremental learning problem is a very challenging task. And we have preliminarily found that class incremental learning techniques need to be carefully specialized for the multimodal case. This is in order for them to work reasonably and acceptably. So our first attempt was to understand whether there is a case in the standard application class incremental learning techniques, and then our next target will be to modify and apply these techniques to the multimodal case. Equally important, in order to evaluate traffic classification performance in incremental scenarios, it is apparent that differential forms of traffic classification metrics are required. In other terms, if we take the F1 score, for instance, as the relevant example, three meaningful evaluation metrics are the drop pool, in other terms, how much lower is the F measure when I train incrementally as opposed to a full retraining. Ideally, I would like to have a drop equal to 0. And also from this drop pool, I can derive two different submetrics, which are drop old and drop new. Actually, they are the same difference, but focusing only on old and new classes. And this is to assert potential issues due to forgetting or intransigence, respectively. We now report the results of the benchmark on a radar plot, which includes the three metrics that I have mentioned. And of course, since these all metrics are drops, the best results are achieved on the outwards of the plot, so toward the zero value. And first of all, for convenience of the evaluation, we have split the methods in two macro classes, named the baselines and the state of art. Comparing the baselines, as expected, we observed that best performing methods are the ones adopting a memory, so the ones that are retaining a part of the old knowledge, and these are FTMEM and FZMEM. Also, by comparing these two best performing baselines in the two scenarios, it turns out that a big increment scenario leads to a more balanced performance across the metrics. Okay. On the contrary, a small increment scenario enjoys a smaller drop old, but a larger drop new. This can be explained as follows. Since we are dealing with the F1 score, a larger drop new implies a very low F1 score achieved by the incremental methods. And this is likely due to low precision and the catastrophic forgetting phenomenon toward the sole new class. So the small increment scenario appears to be much more problematic in terms of the addition of new classes. Compared to the baselines, instead, state-of-art methods have always better performance, recall the lower the better, in both scenarios. However, their performance presents the characteristics which are similar to that of the baselines. This means that the big increment scenario leads to more balanced performance. On the contrary, the small increment scenario incurs higher drop new, and which is again is likely due to catastrophic forgetting. So in the case of small increment, there is much more catastrophic forgetting than in the big increment. And although state-of-art techniques significantly outperform the baselines, and there is a clear improvement, as we can see from this slide and this slide, they still present poor performance in the small increment scenario. Hence, there is a huge room for improvement in terms of design of novel class incremental learning techniques, which are suitably specialized for traffic classification, in our opinion. Now that we have understood how far class incremental learning methods are from full retraining in terms of traffic classification performance, we can now look at the other phase of the medal, which is the training complexity. For this reason, in the slide, I'm reporting the ratio between the training time needed by the generic class incremental learning method, TSIL, divided by the time needed for full retraining, TS. So ideally, we want this ratio to be smaller than 1. And the analysis, again, is reported from the two scenarios. In the big increment scenario on the left, all the approaches result in a total time, in a total training time that ranges from 0.25, 1/4 to 3/4 the time spent by the scratch, by the full retraining. The only exception is represented by OVNs, which is highlighted in this figure, which requires 10 times the training time required by scratch. So not all the incremental techniques in all the scenarios are more efficient than the scratch. This outcomes is justified by the fact that this is a particular model growth technique, which grows the classification structure with the number of classes. I'm not going into the details, but in this particular case, the addition of 20 applications for OVNs requires the training of 20 new one versus rest binary classification models. This is the reason for this huge complexity. In the small increment scenarios, on the contrary, the right plot, we can notice that all the approaches show a total training time, which is in the worst case 20 times lower than scratch time. So this is a huge gain in terms of complexity or training complexity. And this is a huge complexity gain in this peculiar scenario, but I recall you that this is also the more challenging in terms of traffic classification performance. And in this case, the complexity of OVNs is manageable, okay? But this is because, in general, this scenario better enjoys the characteristic of the incremental learning setup. The final side note is that I have divided the training time in SGD and post-SGD contributions. This is to underline that the time needed, that there is a time needed for actual training via the standard, stochastic gradient descent method, And there is also some time that is needed for preliminary and ancillary operations which are required before starting the incremental training phase. So before you start incremental training phase, some methods require some preliminary operations. Okay. And this is accounted in the post-SGD. If we look at the post-SGD contribution, it turns out that in the big increment scenario, the impact of post-SGD is negligible, whereas in the small increment scenario is somewhat higher. And the reason is that these preliminary operations are associated to a starting model which is bigger. Indeed, in the small increment scenario, we have a 39 app classifier to be updated, as opposed to a 20 app classifier to be updated in the big increment scenario. We can now put in comparison the two phases I have discussed, traffic classification, performance, and complexity. This is done with this plot that puts on x-axis the training time and on y-axis the overall F measure, that is the absolute performance. There are two main considerations that can be done. First of all the approaches behave similarly when passing from the big increment to small increment. And there is a general decrease in the total training time, which is reduced by at least one order of magnitude. Secondly, the analysis highlights that the approaches also achieve a general F1 score improvement, moving from a big to a small scenario. The only caveat is that in the small scenario, there is still a relevant gap due to the residual catastrophic forgetting. By focusing on the big increment scenario, big results the clear winner in the 20 plus 20 scenario, with comparable F1 score with respect to Lucir and having a lower training time. On the other hand, in the small increment scenario, the highest training time is achieved by big and events, which also share the same F1 score, which is the highest. So this means that in this scenario, you cannot have methods with the highest incremental traffic classification performance and the lowest training complexity. Hence, to summarize, this webinar has highlighted that multimodal deep learning techniques are the current enabler for state-of-art traffic classification. However, their design is not so immediate. We have discussed the current partial lack of dataset for performing sound experimentation related to mobile traffic analysis. And to this end, I have provided an update on the Mirage project and the corresponding publicly available datasets that are being shared by our group. Third, we have highlighted the performance wall of current state-of-art multimodal deep learning traffic classifiers and the need for explainable AI techniques in their interpretation and reasoned improvement. Finally, we have laid the ground for instilling adaptivity properties in deep learning traffic classifiers whenever new applications or services come in and need to be recognized. Although the results are promising in this case, they have highlighted that there is still a huge way to go. Okay. So this concludes my webinar speech on this topic. I hope you enjoyed it. And for those of you who want to deepen it, I'm collecting a list of references, which provides you more or less the context and also the latest advances from our research group. Okay. I'm now open to questions or curiosities from the audience.
Thank you so much, John, for the presentation. Now let's have the discussion and, of course, answer some questions that are being posted in the Q&A. And if any other participants would like to ask more questions, please type them in the Q&A. So welcome, Vishnu, and good afternoon.
Hi, Thomas, and thank you, Dom, for that excellent presentation. By the way, we invited Dom for the AI for Good Summit. Unfortunately, he couldn't make it. So this presentation is basically in that series. Thank you, Dom, for making the time. I remember your previous presentation with the Mirage project, which we had earlier, and you have. It's quite clear that you have made quite a bit of progress from going from there. Question: Hassan is asking how these algorithms could be applied to real-world wireless problem. I believe you could look at it from a traffic classification perspective. I remember in your previous presentation when you introduced the Mirage, that time you had talked about advertisement and such use cases where traffic classification could lead to such real-world benefits. But I think now you may have more insight into how this could lead to maybe more business use cases or something like that. I want to ask your opinion on how to answer Hassan's question.
Yes, they can be applied. Okay, if you focus on explainable AI tools, these are quite general. So whenever you have a classification problem, you can apply this kind of methodology, especially if your solution is a multimodal solution. So if you have a multimodal deep learning classifier that, for instance, classifies devices via wireless fingerprints, that's the case. So you can both try to understand what's the contribution of portions of the input, and you can use them to improve your deep learning architecture. And also you can also use the techniques that I have described to improve the reliability of these classifiers. If we focus on class incremental learning techniques, this is, of course, much than needed, because every time you have a new device that needs to be classified, you have a new device that you want to incorporate in your classifier, there is a dilemma. Should you keep all the data sets and a large data set and retrain everything from scratch, or you should keep also only your classifier, your model, and just add the new device that you want to fingerprint? This is the case for class incremental learning. But I want to specify that in the framework of continual learning, there are also other incremental learning scenarios, like task incremental, and there is a task incremental in which, for instance, you may want to add another classification problem. For instance, you want to classify the device, and you want also to classify the operating condition of the device at a certain point. So yes, this is quite general, and this could be applied to a real wireless problem. So if you have a data set where you have, for instance, wireless fingerprints, and you want to classify the devices, this may be the right fit for your solution.
Thank you so much, Tom. Joaquin is asking, can you switch between big increment scenario and small increment scenario?
Yeah. This is an interesting question, and this is we don't have an answer to date, because what we have found, of course, our starting point was to take some progresses from computer vision literature, which is the one that is making the most trends in this type of techniques, and we just applied these techniques to our problem. And it turns out that there are fundamental differences between the scenarios that you typically encounter in computer vision and those that you have in traffic classification. So most of the techniques that work very efficiently, very good in computer vision, don't work very well in the traffic classification landscape. So we had to understand, and it turns out that the small increment scenario is very challenging, because the fact that you are adding only one application, or one or two applications, means that you have to retain a large knowledge of all the applications, a very large knowledge of all the applications, and you have to add only one or two new applications. And there is a huge discrepancy between these two kinds of knowledges, the old and new knowledge. And it turns out that most of the techniques that are devised for computer vision, which are usually tested in the big increment scenario, don't work well in the small increment scenario. Like, for instance, ICAR, like Lucir, which are state-of-art techniques in computer vision, but we have found that these are not working well in the typical traffic classification scenarios, where you have a classifier that has been already built, and you want to, like a new app is trending, like 4 years ago was trending TikTok, you want to include TikTok in the traffic classification landscape. These techniques are not working well in this context. So this goes for new techniques, for novel techniques, which are specialized for traffic classification scenarios, or in other ways, scenarios where the number of apps that you are adding are much smaller, the number is much smaller than the number of apps that you already have. So this calls for specialized solutions which are peculiar to that kind of scenario.
Very interesting. Yeah, very interesting. Thanks, Tom. Maybe I can ask one last question. You know, the training time. You have talked about training time.
Yeah.
Why is the training time important? Is it because as the new apps come in, new devices come in, you are worried about retraining? And as you told, you know, is that the case, or is there something else which we are missing? Because normally in network traffic, one would worry about inference time or, you know, real-time applications or something like that. But here you have looked at training time. Is that the scale of applications which worries you, or are we missing something?
You're right, because typically the inference time is the what we have in mind when we speak about network devices. But if you think about the recent trend of trying to train traffic classifiers and algorithms in general on the edge, this becomes very, very important, because this kind of devices have limited computation with respect to cloud computation, and also they have also other caps like memory caps and so on. So it is interesting to understand whether we could provide a cap for the update of these traffic classifiers and be able to train this traffic classifier directly on the edge without carrying out these operations on the cloud. But in general, also, if you want to, and this is for computational efficiency, but in general, also if you want to perform network traffic personalization and you want to share, your model to another operators, and you want to add your applications that you want to manage, and this becomes very interesting, because typically the operators that are buying large models are operators that do not have these resources to train large models. So this is also why we were investigating this kind of complexity aspect.
Interesting. Thank you so much. Yeah. Maybe.
Yeah, we have another question.
Yeah. The type of models which can apply the CIL methods. Yeah.
Okay. The brief answer. Most of the state-of-art techniques can be applied only to neural networks. This is the brief answer. There are some efforts to generalize in incremental fashion state-of-art ML techniques like random forests, but I have not found libraries that could be used efficiently to test these algorithms on traffic classification problems. So if you look on literature, you may find also some techniques that are applied to ML solutions, but these are very rare, and the 99% of techniques that are state-of-art are only applicable to neural networks.
Thanks a lot, Dom. Thank you for answering all the questions patiently. Back to you, Thomas.
Thank you, Vishnu. And I would like to give a big thank you to Dom for making time for presenting and answering all the questions. It's really nice of you. I would also like to thank all the participants who joined the webinar today. We are going to share the recording on the AI for Good YouTube page, as well as the neural network. And we'll share also Dom's slides for people to access them. So thank you everyone for making time. Just one announcement, the challenge 2023 IT AI and Machine 5G challenge is open for participation. So please, you can check our webpage. You can see problem statements that are open. We will open more problem statements in the coming time. Interesting prizes. There are internship opportunities. You have monetary prize. You have certificates and guest researcher position. So there is a mix of many things that you can get as an award for this year's challenge. And interestingly, we are opening more of real measurements, real data sets for these challenges. So please be on the lookout, join the challenge, join us in Slack, and we'll be interested in having everyone join the challenge. And we also have lined up more webinars, more sessions in future. So please be on the lookout on the AI for Good program page. We are looking forward to your participation in these webinars. So at this point, I would like to close the session. So I would like to thank you for joining. And from me and my colleagues at the ITI and Machine in 5G Challenge, I would like to wish you a very good day and thank you. Bye.
Thank you and thanks for attending.
For participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.